Today we're going to talk about a different kind of angles. We're going to talk about inscribed angles, where we've talked about central angles before, where the vertex is at the center of the circle. So if we look at this figure here, at circle O, we notice that we have a central angle, and the measure of that is that lowercase a. And so we know that that its intercepted arc, QA, is also that lowercase a. So now we want to actually try to find the measure of this angle C. And to do that, we recognize that this is an isosceles triangle because we've got two radii that are sides of the triangle. So we know that this other angle in the triangle has to be C as well. And we can recognize that A is an exterior angle. So we know by the exterior angle theorem that A is going to be equal to the sum of the remote interior angles, which is just C plus C. So when we solve for C, we end up getting that C is A over 2. Now, what this shows us is an inscribed angle. And an inscribed angle is an angle whose vertex is on the circle itself and whose sides are chords. So let's take a look at the difference between an inscribed angle and a central angle. So by definition, an inscribed angle is an angle whose vertex is on the circle and whose sides are chords, as I've drawn right here. A central angle is an angle whose vertex is the center of the circle, and then here with a central angle, the sides of it are actually radii. So now let's move on and take a look at some theorems that we'll learn today. The first one is that the measure of an inscribed angle is going to be half the measure of its intercepted arc. So if we look at this picture here, you'll notice that I have a 50-degree angle whose vertex is on the circle itself. And then when we talk about the inscribed angle, we're talking about the angle that's inside the angle, or where that angle meets the circle. And so here we see that the intercepted arc is going to be 100 degrees. And let's take a look at some examples of how we would do this. Why don't you try to solve this right here and solve for x and y and then come back and take a look at the answers. So you should have seen here that x is going to be 20 degrees because it's half of the intercepted arc, which is 40, so half of 40 gives you 20. And then we see, if we look at this inscribed angle that's 50 degrees, we see that the arc that it intercepts is 100 degrees, and you have to do 100 minus the 40-degree arc to get y, which is just 60 degrees. So now I want you to take a look at this particular exercise, number 10. We actually did this before for homework, but it was before we knew about an inscribed angle. Now this angle right here, angle CAO, is actually what they've numbered as angle 2. So I want you to fill out this chart using what we know about the inscribed angle being half of the intercepted arc. So why don't you pause the video and come back and check your answer. So here you can check all of your answers for these particular situations. So we're going to check those before we move on to the next corollary. So this corollary is going to be built upon the theorem that the inscribed angle is half the intercepted arc. And what this corollary tells us is if we have two inscribed angles that intercept the same arc, then the angles have to be congruent. So here if we take a look at this picture, we have this first, we have a green angle, and it's already measured at 35.5 degrees. And you notice here that it intercepts this arc that I'm highlighting in green. Well, then we have another 35-degree angle, and we see that it ends up intersecting the same arc here. And if we use our original theorem, if these angles are 35.5 degrees, then the intercepted arc would have to be 71 degrees. Now, I want you to take a look at this next corollary, and it says an angle inscribed in a semicircle is a right angle. So I want you to pause this for just a moment to think about why that's the case. Hopefully what you realized is that when you're looking at the angle inscribed in a semicircle, if we look at this purple angle right here, you notice that the endpoints are on the diameter, which means that the intercepted arc is this semicircle. and a semicircle has a measure of 180 degrees. So that angle is going to be, the inscribed angle is going to be 1/2 of 180 degrees, which means that that has to be a 90-degree angle. And the same thing is true if we look at the blue triangle. It is also inscribed in a semicircle, which means its endpoints are on the diameter. And again, we know that that inscribed angle is going to be half of the intercepted arc, or half of 180, which gives us 90. And then we have one more corollary here that tells us if a quadrilateral is inscribed in a circle, then the opposite angles are going to be supplementary. Remember, if we're talking about a supplementary angle, then that just means that they add to 180. So here, you could put points around your circle to form your quadrilateral and put different measures of these arcs as long as they add up to 360, and you could test this corollary. But right here, I've already filled out some measures of arcs, and I want you to pause the video in just a moment and figure out what the measure is of each one of these angles, and come back and check and see what I've got for the answers. So you should have found that angle A was 80 degrees. Angle A is an inscribed angle, and we see that it is going to be half of its intercepted arc, which is that 60 plus 100, and half of 160 is going to be 80 degrees. We also notice here that this 80-degree angle is opposite angle C, which we calculated to be 100 degrees, and we see that 100 plus 80 it does equal 180, which does in fact show us as opposite angles are supplementary. And likewise, once we found angle B and angle D, we know that they are also supplementary as well. Okay, so we have another theorem to take a look at, and this tells us that the measure of an angle formed by a chord and a tangent is equal to half the measure of the intercepted arc. Now remember, we were talking about an inscribed angle. That was an angle on the circle that is formed by two chords. You see here that our vertex of this angle is on the circle itself, but this angle is formed by a chord that I just highlighted and a tangent. But this angle is still equal to half of the intercepted arc. So if we look at this angle ATP, so angle ATP is just going to be half of that intercepted arc. So angle ATP is just going to be 70 degrees. And I wrote over here ATR, it's actually ATP. ATP, and that's going to be 70 degrees. So at this point, what I would like for you to do, there are 4 problems. So I want you to work through those and then pause the video and you can come back and take a look at the answers. So now I'll just scroll through the answers for each one of these examples so you can check your work. And make sure that you have done this correctly. All right, there you go. Now you know more information about inscribed angles and how to find their measures within circles.